Okay, so let's go ahead and take a look at the next objective, which is the next test. So you have two different tests in this objective. One of them is called the ratio test, and the other one is called the integral test. So the progression that we've kind of done is we did a few tests in the last objective, and those are the tests you want to try to use first, or try to at least identify first. But I would say, like, when in doubt, do the ratio test. The ratio test would work for quite a few other series. Like, it would work for most geometric series, and so I think that you could probably do most of your stuff with a ratio test. I'm like 80 to 90% sure you'll see a ratio test on your actual AP test versus any other test. Typically you use the other tests to test what we call endpoints, which won't come up until another couple objectives from now. So let's look at the ratio test. If P, so once I evaluate this limit, if that limit is less than 1, the series converges. If it's bigger than 1 or it's equal to infinity, it diverges. And if it's equal to 1, then it's inconclusive and it's start over again. So we hope it's not equal to 1. We do this test when we have factorials and nth powers. So in this case, nth powers. Okay. And what I'm doing here is I'm taking all of my n's and I'm plugging in plus 1 in. Then I'm dividing it by just the original equation. Okay. So now we'll do that. Limit n approaches infinity of n plus 1 squared minus 1 over 2 to the n plus 1. And then because I'm dividing by the original thing, that's the same thing as inverting and multiplying. So I could, as I get, more savvy, I could start off with n plus 1 squared minus 1, 2 to the n plus 1, and then multiply it by 2 to the n. So already do the inverted multiplication part, and that would totally be fine. So now we hope that some things cancel out. So I'm going to multiply this out in the numerator. Limit n approaches infinity, n squared plus 2n plus 1 minus 1 over, now this 2 to the n plus 1 is actually 2 to the n times 2 to the first power. And then this is 2 to the n and n squared minus 1. So now I get the limit n approaches infinity of n squared plus 2n over 2, because my 2 to the n's cancel out. So 2, and then n squared minus 1. So I get the limit as n approaches infinity, n squared plus 2n over 2, 2n squared minus 2. And then this is the definition of a horizontal asymptote. So I do take the ratio of my n squared in the numerator, my 2n squared in the denominator, and I get 1/2. And my 1/2 is less than 1, so this series converges. So we say that the series n is equal to 1 to infinity of n squared minus 1 over 2 to the n converges by the ratio test. Okay? Now let's look at another test, what's called the integral test. So we use the integral test when it's easy to take the antiderivative of something. So I look here, and it's really easy to take the antiderivative of it. So we would do the integral test, which is why improper integrals are really important. I'm going to take the improper integral. So I'm going to change this whole series to the improper integral from 1 to infinity, because I have n equals 1 down here, 5 over n plus 1. Okay, and they want it to be, instead of n, they want it to be x, because you typically take antiderivatives of x, not n. So now, take the limit as b approaches infinity, antiderivative from 1 to b, 5 over x plus 1 dx. This is the antiderivative of ln. Typically, there is a u substitution here, but your dx will be equal to du, so it doesn't matter because u is equal to x plus 1. So this is the limit as b approaches infinity, ln of 5 ln of x plus 1, and I'm evaluating from 1 to b. So I get 5 ln of b plus 1 I forgot my limit part. Minus 5 ln of 2, because I plug in my 1 here and I get 2. As b gets larger and larger, more towards infinity, that entire thing goes to infinity. So this is infinity. So that means that this diverges. So this series diverges by the integral test. And that is it for this lesson.